we're going to take a look at electrolytic cells. In electrolytic cells, we are going to use energy to make reactions happen. And there are two different types. The first thing we're going to look at is the splitting of water. At one electrode, the anode, water is oxidized. We can produce hydrogen ions, O2, and 4 electrons. At the cathode, water is reduced. Water and electrons form hydrogen gas and 2 hydroxide ions. So we should see bubbles at both. But one of the things that makes this reaction unique is that the oxygen, which is extremely reactive, will react with the titanium. So let's take a look and see what happens. Here's my titanium. Here is my zinc. Here are 3 batteries. When I connect to the first battery, I will be using 9 volts of energy on my electrodes. When I connect to the second battery, because these are in series, I'll be using 18 volts. And when I connect it to the third battery, I'll be using 27 volts. So let's see what happens. I'm dipping my electrode in, and you can see the bubbles at both electrodes. You can really see it at the zinc. And you might be able to see something happening here at the titanium. It's a little tough to see, but you should be able to see it better once I take it out. Can you see the color change? Now I'm going to change and switch the batteries so that I'm now using 18 volts. And we'll do that again. These bubbles are bubbling even faster. They're the hydrogen bubbles. And with the higher energy, I made the purple. This happens because the first layer is very thin and light reflects in such a way that our eyes see this gold. But that titanium oxide is also an insulator, so I need higher volts to build up more titanium oxide, and that thicker layer, the way the light reflects and refracts, we see purple. So now we're going to try it one more time with an even higher voltage, 27 volts. As soon as I start moving this stuff. Okay, me, let's go. There I go. Doesn't take very long for this third one to happen because there's such a high voltage. And you can see that with 27 volts, the titanium oxide layer becomes thick enough that our eyes see blue. So that was one way we can use electrochemistry to break apart water molecules. We're not going to do many calculations with that, however. We will do calculations with electroplating. So here, it's a little easier if I use a simulation. So I'm going to choose silver, and I'm going to use 25 amps, and let's see what happens when I close the circuit. Silver nitrate is building. Sorry, silver metal is building from the silver nitrate. Silver metal is building. And you can see that we produced a certain amount of metal, 0.13, about 0.15 moles of metal, and about 1 2/3 grams, about 1.67 grams. Predict what you think is going to happen if I double the amperage? Am I going to end up with more metal, less metal, the same? Let's take a look. Here I have my silver metal being deposited on the electrode. And if you take a look at the slopes, and we're not going to actually calculate them, but the slope of the 50 amp is twice the slope of the 25 amp. Now let's take a look at the experiment a little differently. I'm going to look at silver. Oops, we'll do 50 amps. Silver is being formed from the silver nitrate, and look at the charge of silver. Silver is a +1 ion. Now we're going to go to copper, which is a +2 ion. Fewer moles and fewer grams when we try to deposit copper onto an electrode. It looks like maybe half as much. Yeah, about half as much. And this is about 1 gram, and this is about 3 1/3 grams. And now we'll change and try gold. Now we have gold metal, and gold has a +3 charge in this compound. And we are gold plating our electrode. And you can see that there's fewer moles. Let's see, if we're at 0.03 here, a little less than 0.02, 0.01. Oh, but this switched. Now we have 2 grams of gold. So we have more grams of gold, but fewer moles. That happens because gold has a higher mass. So what we're going to take a look at is the idea that the amount plated is proportional to the amperage, and it's proportional to the number of moles of electrons. Silver uses 1 mole of electrons, copper uses 2, and gold uses 3, because silver is a +1 metal, copper is a +2 metal, and gold is usually a +3 metal. So now we're going to take a look at this quantitatively. If we add enough electric current to a non-spontaneous reaction, we can force it to happen. Experimentally, there was a famous experiment where they called the Millikan oil drop experiment, done by Professor Millikan, who discovered the charge of an electron. And the unit for charge is coulomb. Capital C is its symbol. An ampere, or an amp, symbol capital A, is a coulomb per second. So it's a rate. This important equation, the current measured in amperes, is equal to the charge measured in coulombs divided by the time measured in seconds. So when we know how many amps we have, we're going to frequently use it as Q over T, and we're going to use it as a conversion factor in stoichiometry. Because the other thing that's useful is we know that a mole of electrons has 96,485 coulombs. If you know that 1 electron has that much charge, then you multiply it by Avogadro's number, and you end up with that many. So let's see how we use this. So we are going to use electrochemistry to electroplate a steel spoon with silver. So our anode is silver. It's going to form silver ions because it's being oxidized. Our cathode is the metal we're interested in. So it's the spoon, steel. And the cathode is going to have the silver ions, which were produced on the anode. They're going to be reduced and deposited on the cathode so that we end up with a silver-plated spoon. So we have solid silver at the anode, changing into ions and then changing back into solid silver at the cathode. So our reaction is pretty simple. Silver turning to silver. Sorry about that. But it turns back into solid silver in a different place than where it started. And so if we want to calculate the mass of silver added, first we need to know what is the half reaction as we deposit silver ions on the cathode. So we have silver ions and an electron making silver metal. Then it's stoichiometry. And just like every other stoichiometry problem, or its factor label, just like every other factor label and stoichiometry problem we've done, we start with what we know. And we know we have 45 minutes. We also know we have 1.5 amps, and an amp is a coulomb per second, which means we have 1.5 coulombs per second. Well, if I start with minutes, I have no idea why 1 hour is in there. Let's get rid of that. And I convert the minutes to seconds. Now, I can use this piece of information right here. Because for every second, I have 1.5 coulombs. That's what the current tells us. Now that I'm in coulombs, I want to somehow get to grams of silver. Ooh, how do I do that? Well, I know that grams of silver are related to moles of electrons added to the silver, and they're a 1-to-1 ratio. So if I can figure out how many moles of electrons there are, and I know from Faraday's constant the relationship between coulombs and moles of electrons. So I'm going to use Faraday's constant, and again, I know what goes on top and what goes on the bottom because I need my units to cancel out. So now I'm in moles of electrons, and I know that for every mole of silver, I had to use 1 mole of electrons to make it happen. It asks for mass, which is in grams, but the molar mass is easy. Straight from the periodic table. So I plug all that stuff in my calculator, and I get 4.53 grams of silver. It's pretty obvious that I made this problem up because 4.5 grams is kind of a lot of silver to be plating on a spoon. All right, let's take a look at the second type of problem. First type is you need to know mass, and you start with time. The second is you start with mass, and you figure out time. So again, we need a half reaction. We have aluminum. So how many electrons are needed to reduce aluminum ions? Well, since aluminum is +3, we need 3 moles of aluminum, 3 moles of electrons for every mole of aluminum. So I'm going to start with my mass of aluminum. And the other piece of information I have is my amperes, or coulombs per second. So my mass is in kilograms, but I want to work in moles, and so I'm going to convert kilograms to grams. That's pretty easy. And then I'm going to convert grams to moles using the molar mass of aluminum. Now I'm in moles of aluminum. Moles of aluminum need to turn into moles of electrons. And this is a 3-to-1 ratio because of the 3 electrons right here. What I want is time, and I can use current, which is coulombs per unit of time, but I have to get to coulombs. So I'm going to use Faraday's constant to get from moles of electrons to coulombs. And then I'm going to use the coulombs per second, or the amperes, the current, to get to seconds. And to 3 significant figures, I have 1.12 times 10 to the 5th seconds. Or I can convert it to minutes, or I can convert it to hours, but it's critical that you use your units. Okay, now you try a couple. All right, are you ready to see the answer key? You might want to hit pause while you look at these, but we went from days to hours to minutes to seconds. Right here, here's the amperes. Or the current. Here is the information shown by the balanced chemical equation, because Mg makes a 2+ ion. And here is the same mole ratio, different current, and it specifically said minutes, so I had to give my answer in minutes. And 3 significant figures. Okay, if you have any questions, let me know. You should know enough now that you can try the back page of homework.